Okay, so our second lesson on polynomials is talking a little bit more about the graphs of them and different forms that the equation can come in. So just a couple of these are recap, a couple of them are new. So degree should be a recap from yesterday. So that's the highest exponent on a variable, right? So if we had like something like x cubed minus 2x minus 7 is our function, that would mean that that is degree 3. The other way that we can see stuff is in factored form. So if you guys remember from like quadratics last year, something like this, where the x times the x would FOIL into an x squared term, this one is degree 2. Okay, so it can be in standard form or factored form, but we're looking at the one that would multiply out to the highest degree, and then this would have an x term and a constant term, but blah 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 blah, right? A factor is a component that multiplies together to form an equation, so these two would be factors, and so that should look familiar. Multiplicity is a new one, and it's the number of times that a factor occurs in the polynomial, and it's represented by the power on the factor. Okay, so something like this, x plus 2 occurs once, x minus 1 occurs once, so each of these guys would have multiplicity 1. If we had something like y equals x plus 2 times x minus 3 squared, this factor would have a multiplicity of 2, this one would have a multiplicity of 1. So it's essentially the exponent on the factor. If you guys remember from quadratics last year, these are the x-intercepts. So when we factor an equation, it gives us the x-intercepts. The multiplicity, the exponent on each factor, tells us something about how it interacts and how it intercepts the x-axis. So there's 3 different ones that we need to know. So the first one is if the multiplicity is 1, okay? And basically what that means is that it goes straight through, okay? So if the exponent on a factor is a 1, it's a single 0, that 0 only happened once, that would be something like this, okay? We can have a 0 with a multiplicity of 2, so something like this guy where it's, remember that this is x minus 3 times x minus 3, that factor happens twice. When that happens at that x-intercept, it essentially bounces, okay? A proper word would be it lies tangent to the x-axis. So tangent means it comes close, it touches, and then it goes away, okay? So a bounce means it's got a multiplicity of 2. The last one, I can't spell. The last one that we need to know is a multiplicity of 3. So that would be something like y equals x minus 1 cubed. Okay, if it's got a multiplicity of 3, what happens is a change in concavity. Okay, and what that means is essentially it goes from, if I use pink to kind of outline there and then draw myself some eyes, see how that's a sad face? And then if I use blue to kind of go along the line there, and then I do eyes up top, see how now that's a happy face? So the easiest way that I've ever seen to remember a change in concavity is if we go from a happy face to a sad face or vice versa. Okay, so it changes the curvature. It goes from concave down to concave up. Okay, so happy face to sad face or vice versa. Okay, so that would be of 0 with a multiplicity of 3. We need to be able to recognize those things graphically and then show that in our equations. Okay, so the factored form of a polynomial, so in factored form we can determine the degree of the polynomial, the leading coefficient, the zeros, aka the x-intercepts, and their multiplicity, and we can determine the end behavior. So all the same stuff that we talked about yesterday, just we have to get to it a little bit differently. Okay, so the first thing that we're going to do is state the solutions, which is another word for the x-intercepts, and then the multiplicity of each. While we're doing that, we're going to state the constant term. This is a really common thing that questions ask for, so we're just going to do all of it together. Okay, so If we want to figure out the x-intercepts, we need things in factored form. Okay, so this is a difference of squares, so x squared, the square root of that is x. 9 squared, or 9 square rooted, sorry, gives us 3. 1's positive, 1's negative, and that's equal to 0. From that, we can get x has to be equal to negative 3, and x is equal to positive 3. If we look at these both, these each have a multiplicity of 1, right? Because there would be a little 1 there and a little 1 there. They're each in the equation once, okay? So that means at each of those coordinates, it would just cut through, like straight through that x-axis. So if I wanted to sketch myself a little graph, there's negative 3, there's positive 3. I know because of my leading coefficient, it's going to go up towards the right. My y-intercept is down here at negative 9, and then it's going to go back up through. So we can mark that as negative 9. There's a little sketch of my graph, and it's going straight through at each of those intercepts. The last thing that we wanted to do was the constant. Okay, this one's, it's really easy, right? It's just negative 9, right? We know that because, so the constant, another way to think of finding it is plug. We're plugging in x equals 0 to find the y-intercept. So y could be 0 squared minus 9. 0 minus 9 is just negative 9, right? So that one's pretty easy. We can just see it from this form that the question first gives us before we factored it, okay? This one's already in factored form, question B here. So our constant's going to be a little different, but we'll get to that in a second. This one's got 2 different unique factors, but one of the factor has a multiplicity of 2, so you can kind of think of it as 3 factors. So we've got x equals negative 4, and then we have 5x plus 2 equals 0. This one's a little bit more complex, so I'm just going to solve for it. And then divide by 5, divide by 5. Okay, so we've got x is equal to negative 4 and x is equal to negative 2/5. This one has a multiplicity of 1. This one has a multiplicity of 2. So if we wanted to sketch, and I know that's not part of what the question asked us to do, but I think it's just a good use of our time. If we wanted to sketch this, we would have one intercept at, let's make that 1, 2, 3, 4. So there's one intercept. We have another one at negative 2/5, so that's about there, kind of just left of the x-axis. Because we have, so if we think about our leading coefficient, it's going to be the one on the x cubed term, because we do x times 5x times another 5x, right? Because we could write this as x plus 4 times 5x plus 2 times 5x plus 2. So our leading coefficient would come from the x times the 5x times the 5x. So 1 times 5 gives us positive 25. So this graph would be finishing up to the right. Okay. At this negative 2/5 intercept, because the multiplicity is 2, it's going to bounce, and then it's going to loop back around and slice through that intercept with a multiplicity of 1. Okay, so see, based on our leading coefficient, our intercepts and their multiplicities, we can draw pretty accurate graphs. If we graphed this, this would be pretty dang accurate. Okay, the constant on this one is a little bit harder. Okay, it might show me that my graph is a little bit askewy, but it's close enough. Just depends on my y-axis scale. So the constant, again, we're plugging in x is equal to 0 to be able to solve for that. So it's going to be 0 plus 4, and then 5 times 0 plus 2 all squared is going to give me my constant. So 0 plus 4 is 4. 5 times 0 is just 0. So then we have 4 times 4. So my constant is 16. Remember that that is also my y-intercept. So My x and y axes are just scaled really, really differently, but that is okay. Okay. There's one more thing that I want to point out with these two examples that isn't in the question head, but I think it's important. Okay, so for both of these, the degree of the function is equal to the sum of the multiplicities. And that is always true. Okay, so notice how we have a degree 2 function, right? This would be x squared. Degree 2, we've got a 1 multiplicity plus a 1 multiplicity. That's going to give us degree 2. Here we've got, if we FOILed all of this out, we would have x times 5x and then times 5x again. So this would be an x cubed. Okay, we also know that because the ends extend in different directions. There's a few different ways we can think about that. But when we have x cubed, that comes from the 1 plus the 2. 1 plus 2 equals that 3. Okay, so the sum of the multiplicities gives us the degree. Okay, so that's one other thing that we can think about as we do future examples. So our next example is for the graph of this polynomial function, we're going to determine the following. So we've got 1, 2, 3 different intercepts. Okay, so this is going to be a cubic function because it's got 3 different zeros, all with multiplicity 1, because it cuts through, cuts through, cuts through. We don't have any bouncing. We don't have any changes in concavity. This one's just, a cubic function. Okay, so the least possible degree is going to be 3. Okay, so we see that as 1 plus 1 plus 1. Right, multiplicity 1 plus multiplicity 1 plus multiplicity 1. Why it says least possible kind of gets into like a higher level math thinking, but that's how we ask the question always. If we looked at a multiplicity of like 4, it actually looks really similar to a multiplicity of 2. And so we always are going to assume it's either a 1, 2, or 3. It's never going to be 4 or 5 or 6, even though 4 and 5 and 6 actually look really similar. That's why it's always saying least possible. So we're always assigning a 1, 2, and a 3, even though it could be a 4 instead of a 2 or a 5 instead of a 3. But this one, they're all just 1s. There's no way that it could be a 2 or 4 or 6 or anything like that. Okay. The sign of the leading coefficient, we know because this is going down to the right, that's our end behavior, we know that that has to be negative. Okay. The x-intercepts and the factors of this function, okay, we're going to use our x-intercepts to figure out what the factors are. So our first x-intercept happens at x is equal to negative 4. If I want to turn that into a factor, I'm going to add 4 to both sides. It would be set equal to 0. And then x plus 4 is my actual factor. That would multiply in my equation. So we're going to do that for the 2 other x-intercepts. So then x plus 3 is a factor. And then x plus 2 is a factor. Okay. To determine the equation of the polynomial, and you're going to have to write another line under here quickly or later, so leave yourself some room. We know that this is going to be a product of these 3 factors that we wrote up there, okay? And then we also know that there's a negative coefficient on the front, okay? So we know that because of that end behavior. Now the problem is that negative coefficient might have been a negative 1, but it might have been a negative 2 or a negative 4 or a negative 6 or negative 3/2 or something random, okay? So to check that it is a 1, beep, beep, we're going to check that that is in fact a 1. We're going to plug in a value, okay? So if I go back up to my graph, notice how this point right here is a nice point that's on the grid line. Its coordinates are -1 and -6 because each y is 2 here. So to check if my a value is in fact a 1, or a -1, sorry, not a different number, I'm going to plug that point in and see if my a is equal to 1. Okay, so what I do is I say, okay, y is equal to -6. I'm just going to plug in an unknown a value in there to actually solve for this thing. And then I'm going to put in a -1 for x. So -1 plus 4, -1 plus 3, and -1 plus 2. So we have to isolate what this a value is. And so this should look a little bit familiar because you guys did this last year in Math 20 in the quadratics unit. So we have -6 is equal to 6a, divide both sides by 6. A is equal to that -1. So that means that that negative is just a -1. There's no like -2 or -7 or negative whatever. Okay. The reason why we got to check that a value is a graph that looks like that is just like taller than the graph that we have here, has the same 3 intercepts, and that a value essentially figures out how far away from those intercepts the peaks get. Okay, so that a value, we can kind of think of it as like a stretch, if we stretch that graph out. So we do always want to check for it. Okay, in this case we knew it should be a negative, so when we solve for it and we got a -1, that makes sense in our brain. Okay, so this is actually a better way to do it as opposed to just putting a negative in there. So we're going to go through this one more time later in the examples. Okay, my domain and my range, it's going to go forever left and right, so it's going to just keep going, keep going, keep going, keep going. If I just zoom out forever, it's going to keep going. Same with to the left and up and down. So my domain and range are x is all real numbers and y is all real numbers. I guess I should write this properly. And we can remember that those two things, x is going to be all real numbers for any polynomial, y is going to be all real numbers for any odd degree polynomial, right? So you can just write those as little notes for yourself. That's always going to be true for any polynomial. Because this is odd, we know that right away. We don't have to think about it. Okay, but we also have the picture so we can look. The constant term, okay, so that's going to be my y-intercept. So based on the graph, I should get a negative number, right? It's definitely less than -16, which is where this thing kind of caps out, okay? So the constant term, y is going to be equal to negative, and remember you're plugging a 0 in. So it's 0 plus 4, and then 0 plus 3, and then 0 plus 2. So you have -4 times 3 times 2. So we get -24 for that constant. Okay. I think often the temptation when we're asked for what is the constant term, we want to factor, or we want to multiply the factored form out to get that c value, to get that like constant term that doesn't have the x attached to it, but that would take way longer than what we just did, plugging that 0 in. So it's definitely the most efficient way to do it if we have factored form. If we had the like simplified version, this had already been multiplied out, we could just look at that like kind of last term, the one without the x, and that would be the constant right away. But this is definitely the easier way when we have factored. This next one, it's an empty page. We're going to fill it, not even fill it, but we're going to put some stuff on it. So we're going to determine the equation of a cubic function. So that means that this is degree 3. So we should have either 3 different factors, or maybe we have less than that, but then our multiplicities are different, okay? What it tells us is that p at 3 is equal to 0. So remember that this is my x value. This is my y value. So I could actually plot that as a point. So x is 3, 1, 2, 3. Y is 0, there's my point, okay? So that's an x-intercept. And then it even elaborates and says multiplicity 2. So we know at that point it's going to bounce, okay? So this factor exists twice in my polynomial. Okay, the other point that it gives us is p at -1 is equal to 0. So that, again, my x value is -1, my y value is 0. So there's another intercept. And if it doesn't say that it has a different multiplicity, we're going to just assume m is equal to 1. So it's going to go straight through that x-axis at that point. And it also tells us that p at 0, so when x is 0, the value of the function is 18. So there's -1, 3, and 18. And like we talked about yesterday, we always want to label our intercepts. Okay. So we know that it's going to bounce here. And it doesn't actually say to sketch the equation or sketch the graph, but I think it always just helps to have a picture of it. We know it's going to bounce. We don't know which direction it's coming from. So we don't know if this graph is going to end up or if it's going to end down. Okay, but what we do know is that it's going to bounce here, and then it has to pass through this y-intercept and then come and hit this guy. So if I come from the bottom and it bounces, then I would have to cross the x-axis to get up to this 18 before I was supposed to. So what that means is that we have to come from the kind of top. It's going to bounce. That's going to allow it to go up to 18, and then it's going to come through 18 and come down and pass straight through that -1. Okay, so that tells me, hey, my leading coefficient is positive. Okay, in this case, that's going to be our a value. So we're going to go through that process again. So we're going to start with y is equal to, and it's going to be equal to a times the factors. So this factor is an x plus 1, and it had a multiplicity of 1. And then this factor is going to be x minus 3, and it had a multiplicity of 2, right? Because I said x is equal to 3, move that 3 over, that's where I'm getting that x minus 3. Same with x is equal to -1, move it over, that's where I'm getting x plus 1 is my factor. Okay, so again, to solve for a, we know it's going to be positive, but it might not be a 1 this time. It's not going to be a 1, just to show you guys. So the other point that I know is this y-intercept. So I can say, okay, 18 is y when x is 0. And the y-intercept is generally the easiest way to solve for a, so you might want to make a note of that. So the y-intercept is the easiest way to solve for a, right? Because x is equal to 0. That's a really easy number to plug in. So we're going to have 18 is equal to a times 1 times -3 squared. So that's 9a, because it is negative times negative, turns it into a positive. Divide both sides by 2, and a is equal to 2. So what that means is that my overall equation is equal to 2 times x plus 1 times x minus 3 squared. Okay, and then we can check back and say, okay, it was supposed to be cubic. I've got a multiplicity of 1 plus a multiplicity of 2. 1 plus 2 equals 3. I got that cubic function. My range and domain are both all real numbers, which is what a cubic function is supposed to be. And I can graph this in my calculator and just check all of these things. Okay, so our last example is another cubic polynomial. So this one's not in factored form. So this is going to look really similar to yesterday. We're just going to introduce a couple other things that it could ask. So we've got -2x cubed plus 6x minus 4. We're going to find the characteristics. So my leading coefficient is the coefficient on my highest degree term. So that's going to be this term here. So it's a -2, which if I skip down to C means that my end behavior is going down to the right. So I know this graph is going to be ending kind of like down there somewheres. The degree is 3 because it's my highest exponent on the x, and it's already in standard form, so that's really easy to look at. My domain, again, because all polynomials, they're just going to be x is equal to all real numbers. And then range, because it's an odd function, we know right away that y is also equal to all real numbers. My y-intercept is going to be my constant. And because this is in standard form already, it's really easy to see that it's equal to -4. Remember that you could plug x equals 0 in to find that. And then zeros, those are my x-intercepts. That's much harder to figure out algebraically, so this is when we're going to use our calculator. So I already have it in here, so -2x cubed plus 6x minus 4. I hit graph. It looks like this. So I've got a 0, and like these are nice numbers. Generally, they're going to be nice numbers. But to double check, we can calculate that 0. I'm going to give it a left bound and a right bound, and it's a nice even -2. So we've got x is equal to -2. And just as a note, we're going to say m is equal to 1, so multiplicity is equal to 1. And then we've got x is equal to, the other one was at 1. So again, I could get my calculators to tell me that, or you can go second table and say, hey, okay, at 1, it's 0. At -2, it's 0. So it's another way to figure out those zeros. And because, if we go back to the picture, we can see that it bounces, we know that that multiplicity is equal to 2. Okay, and then 1 plus 2 is equal to 3, which is my degree up there. Okay, and just as we predicted, it's going down to the right. Okay, so we could kind of draw ourselves a little sketch. Here's 1, there's -2, bounces there, it goes through at -4, and it comes back around. You can't see any of what I just did. It's up there. Haha. There's my little sketch. The calculator one is better, honestly. So the last thing that we're going to talk about is the intervals where the function is positive or negative. So positive just means it's above the x-axis, right? The y values are positive, or negative means it's below the x-axis, y values are negative. So the intervals where it's positive is where x is less than -2. I guess I should specify what I'm doing. So P for positive. And then I should have really written that whole word, but negative is basically everywhere else. 0 doesn't count as a negative though. So x has to be either greater than -2. We're going to write this a little bit different. Hold on. It's negative. We look at this graph between -2 and +1, and then it goes to 0, which is not technically negative. So we're going to write it as -2 has to be less than x, which is less than 1, so between -2 and 1, and where x is greater than but not equal to 1. So it's negative all here, but again, not where it's equal to 0. Okay, so positive up here, negative, takes a quick break from being negative, negative again. The maximum or minimum values, well, it depends on, this one just says maximum or min, so it kind of depends on the word relative. So if we were talking relative absolute or relative maximums or mins, we would want to find this relative minimum point. So around all the points that are kind of around it, it's the minimum point, or the relative maximum. So the points that it's kind of sandwiched in between, that's the maximum. But really, the absolute max and min of this function are, it goes to infinity in the positive direction, and it goes to infinity in the negative direction. Okay, so really the max for this one would be infinity, and the minimum would be negative infinity. But we could also do, we could do relative min by punching in using our calculator setting. So the relative minimum is this point here. So compared to all the other points around us, rounded, it's the lowest. So we're going to go second, calc, and we're looking for a minimum. Okay, so it wants a left bound and a right bound. So we want to give it kind of boundaries of where we want that lowest point between. So kind of like that. And then my guess down there, that minimum is x is equal to -1 essentially, and then y is equal to -8. So relative minimum is -8. My relative maximum, same deal, we're looking at that point. We already know it's an intercept, so that relative maximum is 0, and it happens when x is equal to 1. Okay. The intervals where the function is increasing or decreasing, we're looking at the slope. So see how here it's going down, 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 and then right at that relative minimum, it reverses and it starts going up. So this would be decreasing, stop, increasing, stop, decreasing. Okay, so increasing would be between this -1 and +1, so that relative minimum and that relative maximum. So between -1 and +1, and then it's decreasing when x is either less than -1, so all the stuff over here, or x is greater than +1, so we see that decreasing again. So remember, this is like a positive slope if it's increasing, and it's a negative slope if it's decreasing. So those hopefully are all like pretty intuitive things. The big thing for today was that multiplicity and remembering how to solve for that a value, how to solve for the leading coefficient from factored form. Okay, you guys can always check this stuff in your calculator, and if you have any questions, definitely let me know. Okay.